So we did this problem at the end of class, and we ran the ratio test on it. And what we were able to determine was, after we took the limit, that we needed the absolute value of 2x minus 5 to be less than 1. Do you have that there in your notes?
Yes.
And then we went about solving this.
Yeah.
And what did we get? X was...
Less than x is less than 3. Yeah, 2, 3.
Okay, now, do you remember the conclusion of the ratio test? It says...
We didn't actually write a conclusion.
Okay, but the conclusion of the ratio test is that if the limit that we take is less than 1, this converges.
Right.
If it's greater than 1, it diverges. And if it's equal to 1, the test fails, right? Okay, so what we need to do is we need to, again, try and understand like what we're doing here. We're trying to look at this infinite series as a function, and we're really trying. I thought I silenced that. Sorry, hold on. I thought I had silenced that.
By the way, don't ask this. No, he's not going to. What? 12 bonus points.
Okay, this is good. All right.
Hey,
So,
Professor.
yes.
He brought a very good point up.
What?
Are you going to put in the bonus points?
4?
You cursing multiple times.
I'm not sure I did.
Yeah.
Oh, wait, I'll
yeah,
go
you
back in
did.
the video for
There's
those
at least
points.
4 different times.
4 times.
Yeah.
I don't know about that.
I will
Okay.
go back in the video and I will show you.
If we can get through the material, I'll talk about bonus at some point in time. All right, so what we know for sure right now is that as long as x is between 2 and 3, not including 2, not including 3, that this will converge. We still don't know what happens in the event that the 2x minus 5 in absolute value is equal to 1. Because if it's equal to 1, we know that the test fails, right? But it could still happen that this series converges, if this is true. Understand? The ratio test, if it equals 1, we don't know. Less than 1, we're in business. Greater than 1, it diverges, right? So what we need to do now is address this question. What happens if it's 1? All right, so we need to test the endpoints. All right? Now this is something we did not do last class because we ran out of time. All right, in other words, what happens if x is 2? Question. What happens if x is 3? So we'll look at these one at a time. All right? Now, do you all understand that if x is 2, what happens here? 2, 4 minus 5, negative 1, absolute value? We get 1, and that's when the test would have failed, right? Or if we plug in 3 here, we get 6 minus 5, that's 1. And then again, right, the test would have failed. So just because the test failed doesn't mean that it diverges, right? It may converge, may diverge. So we address these one at a time. Here we go. Let x be 2. Okay, let's let x be 2. And let's rewrite the series. All right, so rewrite the series up here. Sum n equals 0 to infinity. Now when I plug 2 in there, I get negative 1 to the n over n. See, it's not the same as 1 over n.
No, that alternates.
It's an alternating series. This is an alternating harmonic. Do y'all remember what this one does?
Yes.
What is it, converge or diverge?
Diverge. Constant over linear,
It's alternating though.
well, then it's balanced.
This converges. This converges. So look, I'm going to run through it real quick. But what I'm getting at is, look, when we run the ratio test, x is a variable, right? and so we have to look at this expression. But in that process, we discovered that there are two endpoints that we need to kind of investigate further. And when we investigate one of them, we fix the x. Now this series looks like a series back in 8.4 or 8.3, where we don't have x's in here anymore. So we're just going to run back through our tests. For this one, I would run an alternating series test. Okay? So for an alternating series test, what are the two things you have to show?
That is
Decreasing, and I need to show it's decreasing. And I need to show that a sub n goes to 0. Those are the two things I need to show. Now, when we're doing alternating series tests, do you remember that what you do is you actually peel off, wait, was it a sub n or b sub n on that formula sheet? Well, let me see. Hold on. Do you have it right here? Alternating series. Yeah, they did use a sub n. So they split off, for this particular problem, a sub n for us is 1 over n. It's the part that's not alternating, right? So is this decreasing? Is a sub n greater than a sub n plus 1?
Yes.
Yes. I mean, we could do that by just doing this. Cross multiply. Cancel out our ends. 1 is greater than 0. Check. We've done this problem. That's why I'm moving so fast through this. It is decreasing. And then secondly, what's the limit as n goes to infinity? 0. Okay? Of 1 over n is 0. Check. So that tells us what? It converges. So that means that when x was 2, it converged, right? So that 2 is actually part of our domain. If we didn't do this part, we wouldn't have included the 2, would we? And that would have been a problem. That would have been a mistake. All right, so I know it converges at 2. I'm going to put it converges.
What about a 3?
And now at 3, let's check out what happens at 3. So at 3, we rewrite the series, but instead of having negative 1 to the n in there, what are we going to have?
1 over n.
Just 1 over n. Yep, 1 over n, harmonic, and that diverges. Okay, so it diverges here. Now, since it diverges, now I'm ready to come up with the final answer for when that original series converges. So here's my final answer for this problem. Therefore, sum n equals 0 to infinity of 2x minus 5 to the n over n converges on the interval 2, 3. So see how I wrote that? Bracket 2, parenthesis 3. The bracket means include 2, right? Now, if you want, you could also look at that this way. Okay?
So you don't include 3 because
Don't include 3 because it diverges there, right? You just want to know where it converges. It goes everywhere between 2 and 3, but including 2. You have to do this for all power series. You have to check, well, I shouldn't say you have to. If you look back in your notes, why didn't we do this on the previous example? I think the previous one was the Bessel function. Was it the Bessel?
Yeah.
Okay, why didn't we check the two endpoints on the Bessel function?
because it's from negative infinity.
Because it was from negative infinity to infinity. It converged everywhere, right? What about the example before that? Why didn't we look at endpoints? It only converged at that single point, that boring one, right? So in the event that you get an interval, you must test endpoints. So I'm going to summarize all of this right now. All right, we're going to have like a nice little summary of what's going on. And this is actually a theorem. Okay, given a general power series, remember this is what a general power series looks like. Remember that little x minus a in there? We say that's a power series about a. So given a power series, there are 3 possible outcomes in terms of convergence and divergence, all right? First one, converges at x equals a only. All right, I don't need the exclamation point. Okay, but that would mean that's the boring one. It only converges if you make this piece 0, right? If I let x be a, this is 0, and then it converges, but it's very boring because that's the only place it converges. The other possibility converges, I'm going to do that one last. Converges for all x. In other words, negative infinity to infinity. That means you can plug anything you want in and it's going to converge. And the last one, I'll put it up here, the third possibility is it converges on some interval. Now, when we say some interval, that interval could look like this. It could be, I want to use different number or letters. I'll just leave them blank. It could be an open interval, meaning that you're not going to wind up including both endpoints. That means you would run a test and both endpoints would fail, like not fail, but both endpoints would diverge, right? You could get what we call a half open or a half closed interval, where maybe the left endpoint you include, but the right one you don't. We just had that happen, right? You could have the left endpoint not included, the right endpoint included, right? And one last possibility, or both endpoints are included. Does that make sense? It's going to be one of those four things. All right, so this is a theorem. It says that for all power series, one of these three things is going to happen. The first example I gave you was this one. Second example I gave you was this one. And then the third example we just did is something like this. Now, we're going to do a little bit more in here, okay? There's a little bit more to talk about in terms of when this happens. So, what's that?
Why is diverge not one of them, like as an option?
It can't. The question was, why is diverge not an option? All power series have to converge at least 1 point. This is it right here. So I guess the divergence you're thinking of, this is that case. It diverges everywhere except a point. All power series have to converge. Somewhere. It could be a single point, everywhere, or an interval. But it's impossible for a power series to diverge everywhere.
Could it be like multiple intervals, like let's say?
No. The question was, could it be multiple intervals? No, it has to be a single interval. All right?
With some bracket.
Yeah. Well, it can't be like, you can't say it's going to converge from 2 to 3, and then also over here from 5 to 7. I think that's what you're asking. Yeah, that's not possible. All right? It has to be a single interval. And because of that, I can state the next thing. There is a number. So this is still within the framework of this third one. There is a number R, capital R, such that if the absolute value of x minus a is less than R, it converges. I'm out of a room, so I have to continue over here. R, capital R, is called the radius of convergence. And we have x minus a minus, okay. A minus R, a plus R is called the interval of convergence. And I'll put this in a different color. Note. When finding interval of convergence, you must test endpoints. Okay, so with this interval of convergence that I put up here, you see this up here? It could be any of these four cases. In other words, it could be bracket here, open here, bracket, bracket, or parenthesis bracket. Understand? No? Okay. But that interval is called the interval of convergence. So let's go back to the problem we just did again. All right, let's just talk about it in terms of this language. For the problem, for this problem, sum n equals 0 to infinity 2x minus 5 to the n over n. Okay, which case did we have? We had three different cases, right? This fell into the third case, right? Yep. Now, what is capital R for this?
5 over 2.
Okay, so where are you getting that from?
That's the radius.
Yeah, how did you find R 5 over 2?
Because what's in the parentheses, it's like how your general form is for an equation.
Mhm.
Graph, you have like parentheses x minus a or something like that. So
Uh-huh.
the coefficient in front of x goes underneath 5, so you get 5 over 2.
Okay, so in the definition I just put up on the board, we said absolute value of x minus a less than r, right? Double check, that's what I had put? Yes? Said there exists a number such that this is true, right? Okay, now for us, we have absolute value of 2x minus 5, right, is less than 1. That's what we had when we ran the ratio test. Agreed? This does not mean r is 1, right? Okay, so what we do to get our capital R is let's pull out a 2 out of this, okay? Because I need to have a 1 in front. See, there's a 1 in front of the x here, coefficient of 1. Let's pull that 2 out. So if I pull a 2 out, I'm going to get absolute value of x minus what? 5 halves is less than 1.
1 half? No.
No, I just factored a 2 out. Yes?
Yes.
And then,
Move the 2 over to the other.
okay, how?
Divide by 2.
Divide by 2. Less than 1/2. Well,
Well, are you able to do that within the absolute value?
what do what?
Are you able to do?
Oh, add the
Right, add the 5.
add the
over
5
2.
half.
Absolute value, you have like
Well, what was our interval? Let's go back. What was our interval of convergence?
2 to 3.
What was it?
2 is less than
2,
Including 2, not including 3.
and then to where?
3.
3?
Not including.
Not including 3. That was our interval, right? Do you remember that?
Yes.
Okay, if I draw this on a number line, here's 2, here's 3, right? I want to include 2, everything in between, but I don't want to include 3, right? Y'all with me? Okay. What is the number that's right in the middle of these? 5 halves, isn't it? 5 halves? This is 5 halves. Now, if I look at this as being like a center, how far out do I go in each direction? A half, right? Right, this interval is 1 wide. And so the distance from here to here is a half. And the distance from here to here is a half. Make sense?
yes.
So our radius of convergence, what we need to do is take this inequality and make it look like this, which means I need a coefficient of 1 on the x. So I pulled the 2 out, right? I divided by 2. And now don't I have absolute value of x minus a less than capital R? So do you see our capital R here is actually 1/2, not 5/2. 5/2 is the center of the radius of convergence. Does that kind of follow?
Yeah.
Okay, so this is 1/2.
And that's going to be a uniform pattern that
Yes.
our A will be the center.
Your A will be the center, yes. The A is always the center of the radius of convergence. But we're not, when you're asked for radius of convergence, you don't necessarily need to find the center. You just need to tell us, what we want to know is really like how wide is this interval, right?
Okay, I see what you're saying.
How wide is our interval that we can
So that's
have
what
convergence on?
capital R is.
That's what capital R is. It's the width of the interval. Now, it's not the width. It's half the width, really, because it's the radius, like a radius. If this were a circle, it's kind of like the radius.
But that particular A means that it's, the radius starts at.
That's right.
S.
This particular A, which the form is x minus a, so a is actually 5/2, would be the center. So let me ask you a question. Right, we've got capital R, right? What's the interval of convergence? So this is capital R. What's for interval of convergence, from here on out, I'm just going to put capital I. Is that all right? So I don't have to write interval of convergence?
Is that
Okay.
what you have to write?
What's,
It converges.
yeah, we already had that, didn't we?
It's just, yeah, that's what
Yeah.
we did. It converges, bracket 2, 3.
It's R minus A or something like that, or?
Yeah, you could do that, but we had already got it, right?
It's like 1/2 and then that,
Pardon?
then 1/2 and then the interval.
A minus R plus R.
Yeah, this, if you notice, this right here is actually a minus r, a plus r, isn't it? Yeah. Yeah. What I'm getting at is you don't actually have to run this formula to get this. We actually just tested the endpoints to get it, right? I mean, we still have to figure out if it's including the ends or not. So if we back up just a little bit, if you're given a problem like this and you're asked to find capital R, do you have to run a test on the endpoints? No, because all you're going to use is this inequality. That gives you radius. Understand? If you're asked for capital I, you must run the test on the endpoints. Okay? So asking for capital I is a stronger, more involved process. Yes?
R only works if it's on an interval, right?
That's right. Well, that was my next point. What were the 3 possibilities? Again,
It was 1 point, then it could be an interval.
1 point, all points,
All
or 6.
points.
yep, there were three possibilities, right? I want you to go back to what you have in your notes. Now that we have this idea of radius of convergence, if it only converges at a single point, what's the radius of convergence? That's right, R is 0. Because your radius is 0. If you're at a single point, you say, how far does that go in each direction? You would say 0, wouldn't you? If your solution, if your interval is all real numbers, what's your radius? Infinity. I know that we don't mean that R is infinity as a number. We just mean that the radius is infinite because you go in both directions forever, right? And then here, R, well, R is R, right? It's some number. This is going to be some positive number.
It has to be a real number.
It has to be a real number.
Can't be put.
Your radius will always be positive, yeah, because it comes from an absolute value.
So could I just put a double stroke R for my number?
For what?
For the third one? No. Because it has to be a real number.
Well, but it has to be positive. So you could say it has to be, it has to be a real number that's positive, right? The way we say real number is positive, we just do a superscript up there with a plus. Huh?
I
What?
was saying it doesn't have to be an integer.
That's right, it does not.
It's 0.5%.
Okay, so let's look at another example, all right? By the way, your homework, I'll tell you what your homework is. Your homework is page... I'll get to it eventually here. It starts on page 468. And it's 3 through 21 all.
468 or
468. Three to 21. For every one of these problems, the instructions are to find the radius of convergence and interval of convergence, which means you got to do the whole thing. All right? So we're going to do this one now. We're doing sum n equals 0 to infinity of -5 to the n, x to the n over square root of n plus 1. For this problem, find I, find R. So we need them both, right? All right, so the first thing we'll do is we'll run a ratio test, okay? When we run our ratio, we're going to do limit as n goes to infinity. And then we're going to do this absolute value. We're going to plug n plus 1 into that, divide that by that right there, right? And hoping that you've actually done some of this already, ratio test. Let me try and do it all. Bless you. I've already done the flipping of the fractions. Where did that n plus 2 come from? That's n plus 1 plus 1, right? Okay. What can I ignore here?
The ends,
You can ignore the -5 n,
-5
the x to the n.
Say again?
It's -5 and x.
Yeah, we're not, remember when we said if there was a -1 to the n, we could just ignore it, because that's just going to become a 1? This is -5 to the n. That's not the same thing. Because when you take the absolute value of that, it's not 1.
It's 5.
It's 5 to the n, or n plus 1. So we need to deal with this a little bit. Don't just cancel these. That's what I'm saying. Like, just because you see negative, don't cancel them. But I am going to do, I will do some canceling, but let's understand the algebra that I'm doing first.
Go ahead and cancel out your xn,
-5 to the n times -5, x to the n times x over root n plus 2 times root n plus 1 over -5 to the n, x to the n. So that's just algebraically using properties of exponents on these two, right? Now I can start canceling some stuff.
Okay, so you want us to show to break it up first?
Yeah, because what, I mean, we really need to
Yeah.
show that.
Is
I was just worried about on a test.
At your own risk. Do it at your own risk. Because if you make a mistake and there's no work, then I'm not gonna know what you did, right? So limit n goes to infinity. All right. What about that -5 that's up there? It turns into a positive 5, doesn't it? Yes? 5. And then, oh, I didn't cancel the x to the n. Sorry, x to the n, x to the n. I still have an x up there, don't I?
Yeah.
Now, I said I like to peel my x's off to the side. So I'm going to put an x out here. That's on top, but I just kind of placed it here because I have no other x terms, do I? It's the only x term. Times, what's still here that has root n plus 1 on top and square root of n plus 2 on the bottom. Yeah, so this one, it's pretty clear that I'm going to have to figure out what this does, right? It's all right? And the way I would do that is, and I guess I'll write it down. I'm going to do L'Hopital, but I'm just going to put the whole thing into a single root. I can do that because they're both raised. Oh, and sorry, I forgot to put, we want this less than 1, don't we? I should have been doing less than 1, sorry, less than 1, less than 1. Back here, don't put equals. Just put less than 1. So it should be that thing. This thing needs to be less than 1. 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 And now when we take this limit, we can go inside the root. This goes to 1, right? So we get 5. 5 and then x. So here's where we are. We have the absolute value of 5x is less than 1.
Okay, you just took the limit of that radical, and that goes to 1?
This goes to 1 because if you forget the radical, this infinity over infinity, just run L'Hopital one time.
Okay.
You get 1 over 1. So,
Yes.
all right? Now, let's start with capital R. For capital R, what we need is to make this inequality look like this. So we need a coefficient of 1 on the x, which I have a 5 on the x, don't I? So I factor the 5 out, and then I divide by 5. Okay? Now, does this look like this?
No.
What's A? A is 0. Do y'all see that? A is 0. Now, we're not asked for A. I'm just pointing that out. It does look like this. If A is 0, then we're there, aren't we? So what is capital R? Therefore, capital R is 1/5. So I know that the radius of convergence is 1/5. This is an interval. It's going to go 1/5 in one direction, 1/5 in the other direction. I still don't know if the endpoints are included or not, though. So now I go about trying to find capital I. Okay, so I've got the first part of this I've done. To find capital I need the actual interval right now. So take this inequality, and remember how to convert the inequality out to just a regular inequality with the absolute value, get rid of it. You go what, negative 1/5 less than x less than a fifth? We talked about that last class. So I know right now that my interval looks like this, negative 1/5 to 1/5. If you box that up and move on to the next problem on the test, you're going to miss, I'm going to take off at least half credit right there. Because you still haven't tested endpoints, right? So now let's test the endpoints.
Because we need to know.
So, and this is a question, like, I know this is good, at least this is good, right? For sure, but do the endpoints get included? So now, I'm testing x equals negative 1/5, and I need to test x equals 1/5. So I'll just start with negative 1/5. Let x be negative 1/5, and let's rewrite our original series, replacing the x with negative 1/5. Summation n equals 0 to infinity, negative 5 to the n times negative 1/5 to the n, all over square root of n plus 1. Since these are both raised to the n, I can put them together, right? And when I put negative 5 and negative 1/5 together into a single,
You get 1.
I get 1. And 1 to the n is just 1, right? You understand what I'm doing? I'm putting negative 5 times negative 1/5 to the n. That's the same as this. But negative 5 times negative 1/5 is 1, and 1 to any power is still 1. Make sense?
Yeah, so it's just 1 over.
N or 2n?
Pardon?
Is that n squared or 2n?
No, it's just n. We're not raising something to a power. It's like when I do x cubed times x to the third. That's the same as x times x. Now this is not a good example, sorry. X times y squared is the same as xy squared. So the 2 can go here and here, right? And then it would turn to this. I'm going backwards. I'm going from this to this. Okay, so do y'all agree that the numerator is just 1?
Yeah.
Would you run a comparison test after that?
Well, yeah, that's what I was going to ask you.
Yeah, you can
What does that do? You want to compare that to a p-series? Because, yeah, it's not exactly a p-series. It's real close, right?
run a root
You could do comparison test. You could do limit comparison test. You could do anything you want.
Nth test?
The what?
Nth test?
Nth term test.
Yeah.
If you do the nth term test, this goes to 0, which means the test fails. So how do y'all want to test this?
Let's do comparison.
You want to compare it?
Yeah.
What do you want to compare it to?
1 over n to the 1/2.
Okay, all right, I'll go with that. Now, do you understand that you have to do all this? Like in a problem, like when you're showing me your work, you have to now tell me what you're going to do. So for this, I'm going to do a comparison test. Okay, I'm going to take this series and compare it to which series? You told me you wanted a p series. 1 over n. We'll go root n, which, yes, is 1 over n to the half. 1. Hold on. Be careful here. I'm going to go 1 to 0. I can't go 0 because it would be undefined. But it's okay because we're only talking about one term. It's not going to make a difference in terms of convergence or divergence.
Just solve it.
All right, this is a p series, right? P is a half, right? Which is less than 1, which means this does what? Diverges. Okay, I'm going to compare this to a divergent series, which means I now need to show what? Need to show, but how do I show that? Need to show, or want to show, however you want to do it, that if this right here is our a sub n, I want to, and this right here is our b sub n, I want to show that what? Is greater than or equal to b sub n. If these guys are always bigger than these guys, then that sum's got to be bigger than this sum, and if this sum's diverging, that one's diverging. That's what the comparison test told us. So let's check it out. Is 1 over square root n plus 1 greater than or equal to 1 over root n?
Yes.
We have to be out
Do the cross multiplication.
It's not going to work.
No, it's not.
Just think about it. Which denominator is bigger?
The left one.
Left one. If this denominator is bigger, this fraction's smaller than that one.
That doesn't work.
That comparison didn't work. Well, it's okay. We have other tests,
What if we,
right? So, fails. It's okay to fail.
Couldn't we also make that one bigger?
How?
Or wait, no.
yeah, that's what I was thinking, but then you run into the same problem.
Could we do a limit comparison test, or will it still just?
I like limit comparison. That was the first thing that came to mind when I saw it.
But if we do that, is it going to just put us in the same fail, or?
Let's try limit comparison. Okay? Do y'all understand this kind of fail? Yes?
Can we change it to 1 over 3n to the half?
Yes, you could. Yeah. Now, how would that save you if this was a 3? Because then even if you do like a cross multiply, is 3 root n bigger than or equal to this all the time? I mean, you have to show that algebraically eventually, but algebraically, is it easy to see here?
No.
No.
I mean, you can show it.
Let's try limit comparison. So you want to keep it with the same thing? You want to compare it to the same thing? Let's try comparing it to the same thing, but let's run limit comparison. And what is limit comparison? We need to run limit n goes to infinity of what? A sub n over b sub n. And what are we hoping for?
Some stuff's going to cancel out.
That it turns out to be positive constant, right? Not 0, not infinity. Y'all know which one I'm doing on the table here? This is comparison, the third one, right?
Oh, it is.
It's comparison, it's the third one on there. So I'm going to do 1 over root n plus 1 over root n. Whatever happens, if this turns out to be a positive constant, whatever they do, they both do, right?
Yes.
Okay, so let's flip it around, clean it up. It's going to come out right away here. Root n over root n plus 1. You can put that into a single root. And when you run the limit on that, this is very similar to what we did a minute ago. Infinity over infinity on the inside. L'Hopital on it one time. You just get 1, don't you? And root 1 is 1. This is 1. This is a positive constant. Therefore, whatever they do together. So what does it do? Therefore, that sum, n equals 0 to infinity, of 1 over root n plus 1 diverges. Now, what does that mean? Right? Because this one diverged. We were still comparing it to a divergent series.
Just to a single
That
point.
number isn't in our interval.
This number, okay, what number were we testing here?
Negative 1/5.
We were testing negative 1/5, right? And it turned out at the end of the day that new series at negative 1/5 diverged, which means we don't want negative 1/5 in our answer.
But now we gotta try out 1/5.
Now we have to test 1/5. So
Maybe we
the
should
conclusion
go
of
ahead.
this is that this interval that we were questioning earlier, that this right here is good, right? The parenthesis is good. We don't need a bracket here, right? I mean good as in leave it like that. Not as good as in yes, it works. I'm not trying to confuse you, all right?
Wait, it does work.
Does it? No, it
Well,
did.
after we ran the test.
Yeah, the test worked, but the conclusion is that negative 1/5 is not in our interval of convergence. All right, good.
Wasn't that good?
Leave as open here. Open meaning as a parenthesis. All right, now let's test 1/5. Let x be a fifth. And go into your original series again. Sum n equals 0 to infinity. It was negative 5 to the n, but now 1/5 to the n over root n plus 1. Now when you put those two together, it's not 1. It's negative 1, and that means you can't get rid of it. So it's an alternating series. So I'm going to run the alternating series test. And I'm not going to run it. It works, okay? You're going to show it's decreasing. You're going to show that it converges to 0, and that's pretty straightforward.
Yeah.
Okay? So what does this mean?
It includes 1/5.
It includes one. Therefore, that sum converges. So now our final answer. Our interval convergence is negative 1/5, 1/5 with a bracket. There we go. So you can see how theoretically I could give you a power series problem that would include you having to run 2 different types of tests on each of the endpoints, right? So I can almost make these power series problems in some way incorporate 8.4 without having to ask you a question from 8.4, right? It's embedded in here now. All right.
So these series used to be called power series until they came up with this power series.
You know, that's a good question. I'm not sure. I'm not sure. I was pretty proud of myself yesterday in my college algebra class. I've got a bunch of pretty young students in there, you know, fresh out of high school. And I actually did a poll earlier in the semester to see how many of them had iPhones. And every single one of my 26 students in that class has an iPhone. Not a single Android user. I'm the only Android user in that class. So anyways, yesterday we were doing a discussion about exponential functions. We were talking about Chernobyl. And
We always try to watch them.
I wanted to get some information about Chernobyl that I couldn't remember. So I said, okay, you can take out your phones and look up this. And I had them look it up. And I was so disappointed in them. I mean, like, for a generation that lives their lives on phones, Like I sat there waiting for them. Finally, I had to pull out my phone. I got the information, but it was,
They're
you know,
all trying to use Siri.
either, I don't know. Yeah, they were probably like updating their status on something, but.
Had to plug their phone in because the battery. Or
No, but I was proud that I was able to out search a some kid. Okay, that's it. Power series, you're on your own now with that. Okay. Have fun with all those problems. I think you will find my homework solution videos very beneficial on this section because each problem is going to be unique in the algebra, in the limit that you run. Okay. Y'all understand, though, the process? What you're hoping for, if I were you, what you're hoping for is when you run the ratio test, that you don't get an interval. Because then the answer is either going to be in like all real numbers or a single point. If you get an interval, well, you got a lot of work ahead of you still, right?
How long was
I don't know how long the video was. I know that it took me several days because I just watched it a little bit before I came to class. And I had like 3 different shirts on, I think, during the thing. So it took me several days. All right, 8-6. Representing functions as power series. So the goal of this section is to take a look at a function that maybe we've looked at in the past and somehow represent it as its power series. All right? So I'm not going to be giving you a power series and saying, hey, does it converge or diverge? Instead, I'm going to give you a function and say, hey, rewrite this as its power series, in its power series form. Now, within this section, we're going to be very limited in terms of what functions we can actually turn into their power series. We're going to be restricted. These functions are going to be very carefully selected for you so that we can do this. But in the next section, we will open it up and we will be able to take care of practically every function. But that's next section. All right? So first things first. Remember this very important formula. Recall that when we have sum n equals 0 to infinity of x to the n, this was 1 plus x squared plus ... forever, right? You recognize that from last class? Yeah. That's that geometric series. It's a power series, but it wound up being a geometric series. And when it converges, what does it converge to?
That's a good question.
What does a geometric series converge to when it converges? What number, though? You have a formula for it. What does a geometric series converge to? A over 1 minus r, right? And if you look back from class yesterday, when I did this example, a was 1 and r was x. So this converges to 1 over 1 minus x if the absolute value of x is less than 1. We did this last class, so you can go back and look at it. That means that if I ever see something like this, I can convert it to that power series. Right? Notice that this expression right here has no sums in it or anything like that, right? But if I see this, I can turn it into an infinite sum, as long as the absolute value of that number is strictly less than 1. All right. With me? Do my first example. Express 3 over 1 plus 5x as a power series. So I'm carefully picking an expression. You know what? Let's put f of x in front of this. That way you look at it as a function. Express this function as a power series. Well, for this section I said we're very limited, right? The only thing we can ever really work with is something that looks like this. If it looks like that, we're in business. We can convert that to a power series, right? And more generally, if I want to kind of make this a more general formula, it kind of follows what's in the back of your book, those formula sheets, I could, instead of using x, use u. And let you know, the idea of u is that it's more general than x. And then this would become sum n equals 0 to infinity of u to the n. Understand, these are the same exact formulas. This is basically a dummy variable. So if I look at this right here, maybe I can in some way turn it into this. So let me do some algebra here. How about this? 3 times 1 over 1 minus negative 5x. How about that? Is that the same thing? 3 doesn't matter, I just pull that out. 1 over 1, and then plus is the same as minus minus. And now it kind of looks like this, doesn't it? But my u here, right? What's my u?
Negative 5.
My u is the negative 5x, right? Understand that? So according to this formula, this should turn into 3 times the infinite series n equals 0 to infinity of what?
Negative 5x to the
Negative 5x in parentheses to the n. Now, we're not done quite yet because we want to convert it to a power series, don't we? What is the general form of a power series? Yep, you've got to have sum n equals 0 to infinity, c sub n, x minus a to the n, right? Right now, you don't have x minus a to the n. You have negative 5x, right? So how can I get that negative 5 out of there and just get a coefficient of 1 on the x?
Set up the absolute value or whatever and factor it out?
Not running a test or anything, so I can't just bring in absolute value. How about this? Don't make it harder than it has to. Let's do this. Factor it out. And when I say that, this is what I mean. Isn't that the same thing?
Yes.
Yes? Okay, does it look like this now?
How come we brought the 3 back in?
We didn't have to. I brought it in just for,
Shits and giggles?
yep, just to have it. Because this doesn't have a constant out front, right?
No.
So what I did, look at this right here. This piece right here, isn't that my c sub n? Isn't that the number that's in front of the power of x that keeps changing as n changes? That's what this was. This was always some number in front that changed. Then what about this piece? That's right. This is x minus a to the n. What's a here?
0.
0, right? Now we're missing something here that's critical. When we switch this over to this, using the formula, do you remember the condition we have for that formula to be true? The absolute value of x has to be less than 1, right? Or in terms of this problem, the absolute value of u needs to be less than 1. What is u? What was u for us? Negative 5x, right? So when you say that this is true and that this equals this, you put here at the end for absolute value of negative 5x less than 1. This only holds in this case, right? Let's clean this up. Isn't this the same as absolute value of negative 5 absolute value of x like that. Splitting up, you can do this with absolute value split into 2. And then what's the absolute value of negative 5? 5. Absolute value of x less than 1. Divide by 5, you get 1/5. In other words, here's my final summary of what the heck I'm trying to say here. This function, f of x, is equal to the sum, n equals 0 to infinity, of 3 times 5, no, negative 5, 3 times negative 5 to the n, right, times x to the n for absolute value of x less than 1/5. And when we're using geometric series, which is really what we're doing here, this inequality is always strict. It's never the included, it's never less than or equal to, all right? You have to remember kind of what you're doing. You're not running a ratio test here. You're using the series formula. All right? So that means if you give me a number right now where the absolute value of it is less than 1/5, like let's say 1/10, all right? If I plug 1/10 in here, what would happen? So what is f of 1/10? So let x be a 10th, which is obviously less than 1/5, right? So I'm good? Then f of 1/10 is equal to 3 over 1 plus a half, which is 3 over 3 halves, which is 2. Right? That's 2. What we're saying is that if you put 1/10 right here, if you did, and you did that infinite sum, it would converge to 2. So these are equivalent. Now I know you're asking yourself, why in the world would I ever want to take something so nice and clean and easy and convert it into an infinite series? And the answer is that there comes times when going to the infinite series is actually better than leaving it in its explicit form. Believe it or not, that's when you have to take complicated functions and multiply them together. We convert to the series into it, and it becomes easier to integrate and differentiate. So imagine I asked you right now, this is to kind of give you kind of a feel for what's going to happen. What if I asked you right now this problem? Integrate that to integrate that.
Bounded over linear, so.
You might be able to get this with integration by parts, okay? You might. I can make it a little more complicated, maybe sine squared up there. I could make this integral tough for you to do, or impossible for you to do. So what you would do is you would split it up. Like this, right? Then you would rewrite this as its power series. You'd rewrite this as its power series, which we haven't done yet, but this does have a power series. You'd write them as its power series. And then you would multiply the two infinite power series together to create a new power series. And then you would integrate that power series.
Is that what our calculators do?
Basically, yes. That's why it's useful. I know right now it's like, well, why turn that nice, clean expression into something nasty? Because when you're trying to integrate something nasty, sometimes you can split it up into nicer parts, convert to power series, multiply power series, and then you're off to the races. All right? All right, let's try another one. Forgot my watch today. Yeah, I have 5 minutes. Yeah. All right, how about this? F of x equals 5 over 4 plus 3x. Maybe we'll make this one minus. Let's make it minus. The other one was plus. Give you an example of both. What you're trying to do is get this to look like that, right? That's what you want. So let's get that 5 out of there because it's just causing trouble, right? 3x. All right. What else is causing a problem? The 4, right? The formula doesn't have a 4 here. It has a 1.
We can just divide by 1/4.
Yep.
So it becomes a 5/4 out there.
I'm gonna pull the 4 out. I'm gonna do it a little slower than you're doing it.
Sorry.
That's all right. Right? I can pull a 4 out of the bottom like this, factor it, and then pull that 4 completely out. 5/4 times 1 over 1 minus 3/4 x. Make sense? Now, are we there? I think we're there, right? This right here is going to be, I'm going to use u from now on. So that's our u, right? So long as the absolute value of that is less than 1, we can rewrite this. Well, no, because we don't know what x is. So that'll always give us some sort of like constraint on x, but it won't be like, oh yeah, that's, you know what I'm saying? Because x can change.
Yeah.
So if I let x be 8, it's not going to work. Okay, so now I have this. This equals 5/4. I'm going to leave this outside the sum for, outside the sum for now. N equals 0 to infinity of what? 3/4 to the n. 3/4 x to the n. Right? The whole thing, the whole u to the n. And now I'll do some additional cleaning up here. I'll push the 5/4 back in there, even though I don't have to. And then I'm going to split that up. At 3/4 x to the n, 3/4 to the n, times x to the n. And that's your power series right there. Now this works when? For absolute value of 3/4 x is less than 1. Pull your 3/4 out, multiply by the reciprocal. Four-thirds? I'm just leaving that little algebra for you. It's not that complicated. Pretty good, huh? Not bad. Almost fun. Okay, x to the 5th over 2 plus x.
No, we don't have to do that. This is just, we're just converting into that.
Okay, we have a little bit of a problem on this one. And it's that x to the 5th power up there. Right?
Are we going to separate it to?
Yep, we're going to split it up.
If you had the natural log function with that x to the 5th, would you take it out too?
If it was a natural log of x to the 5th?
Yeah.
Yes, I'd pull that out. Is that okay?
Yes.
Oh, I mean, are you okay with that? Is what I meant. Yes?
I mean, define okay.
I'm kind of out of room, so I'm going to just, I pulled that 1/2 out. That 2 on the bottom is 1/2, so I'm going to go 1/2 x to the 5th, and then 1 over, what do I need to change on the bottom? Minus -1/2 instead of +1/2. And that should be our u right there. See how I pulled that 2 out here and just pulled it out as a 1/2 and just pushed it out in front of the 1/5, or x to the 5th? So there's our u. This is our u. But it's only this piece that gets rewritten as the series, right? We still have a 1/2 x to the 5th out in front. So we have 1/2 x to the 5th times the infinite series n equals 0 to infinity of -1/2 to the n x to the n. I already split them. I already split them for you, all right? So I'm plugging in -1/2 x here, but then I split it up.
I guess if you wanted to, you could push that 1/2 back in.
So you have 2 as the x over.
What am I doing here? To the
I don't
n?
know what we're doing there. 5. Yeah.
What happened here?
Well, you just pushed everything back into your summation.
1/2 went in here, and I put it here. I cannot combine those together, right? Because you have to do this first. So
Yeah.
that's stuck. And then here,
It's the same things.
x to the 5th. The reason I can move the x to the 5th into the sum is because x to the 5th is not controlled by this. N is changing here, right? X to the 5th is just held, right? X is like a fixed number. X to the 5th will be the same. X to the 5th will be the same in every single one of these sums, right? N changing doesn't change that, so I can bring it in. And then when I bring it in, I put it next to this, and I add exponents, and I get this. Right? Okay, that's our power series. And just to do it, let's write out the first few terms of these. I haven't done this, but we could have done this for every one of these. Oh, I forgot something. I need to tell you when it converges. For absolute value of -1/2 x less than 1, which means the absolute value of x has to be less than 2. So as long as you give me a number that's absolute value is less than 2, then this is good. All right? But I wanted to write out the first few terms. So let's plug in 0 for n. This to the 0 is 1. This to the 0 is x to the 5th, and I had a 1/2 out there, right? So this is 1/2 x to the 5th. All right, now let's plug in 1. We plug in 1, we get 1/2 times -1/2. That's -1/4 x to the 6th. -1/4, sorry. X to the 6th. What about the next one? Plugging in 2. 1/2, -1/2 squared. Positive 1/4 times 2, 1/8. 1/8 x to the 7th. And so on and so forth. Next one should be -1/16 x to the 8th plus ... That's your power series. That's your infinite series for that.
Now, you wouldn't like give us that series or that summation in that form and be like, oh, okay, now work backwards.
Go to this.
Yeah.
Well, we should be able to generate a formula, right? From this, we could generate a formula.
I mean, but time constraints for test.
I'm trying to think. I don't think there's going to be a problem where you have to. Well, I don't know. Let me hold off on that. We're going to be doing so much manipulation of series coming up here that I don't want to say you're not going to ever have to turn that back into its formula.
Well, I was just saying no.
Yeah. Yeah. Time constraints. What time constraints? I got all the time in the world. Oh, on a test. You have 3 hours.
Sir, for proper notation,
Uh-huh.
when we're configuring for the sum, would it still be equal, like f of x equals and then until we get to the summation? Like
Oh, you can continue. You can continue this equality the whole way, as long as you include this. Okay, you have to include this,
Okay.
right? This function right here
Yeah.
is defined everywhere, right, except -2,
Okay.
because you get division by 0.
Yeah.
But this is also equal to this summation, so long as the absolute value of x is less than 2,
Okay.
right? So it is okay to write equality the whole way as long as you include this, yes. Because these two are not the same. This right here is not the same as our final answer for x equals 3.
Okay.
Okay?
Yeah.
So that's why we need this. Was there another question? Okay, this next one we're going to turn the screws. This one's going to be weird. I usually have lots of issues right here when I get to this example.
We paid you to sit.
Oh, you know what? But the good news is before we do it, I have to put a note up here. And how much time do we have? 30 minutes? Perfect. All right. Term by term. Term by term differentiation. This is a theorem. If you have a power series with capital R bigger than 0, that means that you have a radius of convergence, right? It's not converging at a single point. It's either all everywhere or an interval. Then, let's see if you agree with this. I can define f of x to be equal to c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus c sub 3 times x minus a cubed plus c sub 4 x minus a to the 4th plus, I'm going to keep going, c sub 5 x minus a to the 5th plus dot, dot, dot. Then this function is defined, right? As long as we're on the radius or within the interval of convergence. This is a well-defined function. Isn't this just that thing expanded out? Like I plugged in 0, plugged in 1, plugged in 2, plugged in 3. All right? Then what's the derivative of this?
With respect to what?
X.
Okay.
Okay? And we get that the derivative of this function with respect to x is, well, what's the derivative of this? That's a constant, right? So that's 0, okay? What's the derivative of this piece right here? Constants here, right? So bring the constant down, right? Derivative of this is what? 1, right? Because a is a constant. So don't we just get c sub 1 plus, now the next one. So you have to do some chain rule here, right? This constant's going to come for the ride. This 2 is going to come out. So we're going to have plus 2c2.
Yeah.
And then x minus a to what power? To the first power. Y'all agree? What about the next one? C sub 3 is a constant. It comes for the ride. 3 comes out. 3 c sub 3 x minus a squared, right?
Would it be going into, okay, never mind, it says chain rule 1, never mind.
Yeah, oh, chain rule inside, yeah. Every time I'm doing chain rule here, the 2's coming out. I'm taking the derivative of what's inside, but that's 1. And that's going to be that for all of these. So the next one, 4 c sub 4 x minus a to the 3rd. There's a pattern here, right? 5 c sub 5 x minus a to the x minus a to the 4th, not x minus 4 to the 4th.
You don't really count C sub 0.
Yeah, so c sub 0 went away, didn't it? I'll do another one. Okay. Plus dot, dot, dot. Questions?
Why would you take the derivative of that?
Oh, you'll see.
Series or power series?
You'll see. You'll see. All right, so got this? Now, I want to do something here. We started out with the formula, right? That was our function. And then I rewrote it, right? In its expanded form. Then I differentiated that and wrote what the derivative of this would be in its expanded form. Take it back to a power series now. Take this back to a power series. Turn it into a sum. You ready to turn that back into a sum? So I need to continue here. Yeah, we need to pick up on the pattern. So what's the pattern we have here?
Is it possible to just take the derivative while it's in its summation form?
Yes, it is. But I need to convince you of that first. That's what I'm trying to do. I'm trying to convince you of it right now. Okay? So what would this formula be? This would be, so I'm continuing from here. This right here is equal to sum n equals 1, right? Because where does this thing start? C sub 1? N equals 1 to infinity. Now what's happening here? Let's take a look at what we've got going on. I've got 1, 2, 3, 4, 5. So I'm just counting, right?
Yeah,
So that should just be an n out front. And then C sub what? N. And then x minus a to the n minus 1. Good. Did y'all see that pattern there? The powers on these things
Yeah, so if you take
start out, you can really look at this first one as being c sub 1 times x minus a to the 0, right? Because that's a 1, and so
if you taking the derivative of that's it because of the
close. There's one thing that's off, and that's what I really want to point out, okay? All right, everyone got that formula? We're good? Okay, so now let's just take a look back. Here's what we had.
well, right, minus the one that's different.
If we have this, if f of x equals sum n equals 0 to infinity, c sub n x minus a to the n, if our original function was written as a power series, then the derivative of this, right, function is equal to sum n equals 1 to infinity of n times c sub n x minus a to the n. Right?
Yeah.
Agreed? N minus 1, sorry. N minus 1. Yes?
So every time we take the derivative again, will it just move the n?
Okay. Yes, so the question is, can we take the derivative of just the power series without having to rewrite it, expand it out? Well, if we were thinking about it, ignore the sum. If I said take the derivative of this, you would say c sub n is a constant, right? Yeah. You would say I have something to a power n, I need to bring the n out, right? So you'd bring the n out. There it is. Then you would need to subtract 1 from inside, from the exponent, which you would do. And you would take the derivative of what's inside, which would be 1, and that would be out here, and you don't need it, right? So this is basically what you would think it would be. It's the power rule, right? Except one thing. Your index shifted. Your index has been shifted. You're not starting at 0 anymore. You're starting at 1. You have to remember that when you take a derivative. Yes?
So if you take the derivative of that again, would it shift up another one?
If you took the
If you
derivative
took
Yes.
the derivative of that, so then n would equal 2.
Yes, if you took the derivative of that again, your index would shift.
So f double prime, right?
F double prime. Yes.
Yeah.
You would have to do it again. Okay?
Oh, so would the n then indicate how many times you've already taken the derivative of that?
No.
Yes or no?
You can put n wherever.
I suppose it could.
Not to jump too far ahead, but isn't it the difference between Taylor and Maclaurin where it starts? Didn't we-
No, that's what that's A is what determines Taylor and Maclaurin.
Not the n equals.
No, it's this number right here. If it's 0, then it's Maclaurin. If it's A other than 0, it's Taylor.
Okay.
All right. Time to see. I keep on looking for my watch. I don't have one. Here we go.
So now if we take integral of that, we just then go down.
We'll do integration next time. We're not going to be able to get to integration.
Oh,
That's crazy.
express as a power series. Express this as a power series. And do something I haven't done in a while. I'm going to pass around your sign-in sheet. What is today, the 20th?
Yeah.
Hey, 420.
I was, well, I won't say that, never mind. Never mind. I have a bunch of papers here. If anyone has stuff they want to pick up from me, I've got a bunch of stuff up here. But come get it after class. Okay, express this as a power series. Yes?
Would you just take the derivative and then like divide by n and then add 1 to the next one?
Take the derivative of what?
Express and power.
Well, the derivative is probably going to come into play, but the...
Would we have to expand that out?
Okay, this does not look like this yet, right? Our formula does not have all of this squared.
Is that why you're
Right.
gonna take the derivative so you can knock that power down?
If we take the derivative of that, it's actually going to get uglier.
Yeah.
Yeah.
You can just rewrite that as 1 over 1 minus x all to the second power.
Basic use of would work.
Right?
You could, okay, so there's a couple things I'm hearing here. Let me try and address these. First, I'm hearing we could rewrite this as 1 over 1 minus x, all of it squared, which would be true. And let me just write this out. We're not going to do this, but let me just write it out. This would mean sum n equals 0 to infinity x to the n squared, right?
Yeah.
So that would be legitimate, but you need to write this as a power series, not a power series squared. So you need a single, like, final power series, which would mean you're really trying to do this power series times another power series itself, right? And, okay, we're not ready to go down this road yet, all right? This is not as clean and easy as you would think. Although it's not that bad, but we're not going to address that this way. Now, if we look at this as, you might say that that's equal to 1 minus x to the negative 2, right? That's what that is?
Yeah.
And then you could say take the derivative, but if we take derivative, do you see how that gets more complicated?
Yeah.
Becomes negative 2, all of,
Negative
well,
3.
it's actually, that's the derivative of that?
Negative. Negative.
Hold on,
Yeah.
minus,
Because you take the derivative, that negative 2 pops
Yeah,
out.
it's minus 2 here. Negative 2.
what the heck am I doing?
Oh, okay, then the negative
Two-
pops out.
Yeah, like that?
But then the negative and the answer
Okay,
pops out.
who
So
cares?
you're right,
Who cares? I don't even feel like thinking,
Just
huh?
expand that out? Could you just expand it to 1 minus 2x plus x squared? Or would that not help in any way?
Okay, so we could expand the bottom out like that, but how does that, we can't use this. See, we're still very limited. We can only use this in this section. So we can't get that to look like this because,
1 over 1 minus x times 1 over 1 minus x.
how about this? How about this? Okay, this is why I said students have a little bit of trouble with this. This is what we do know about, right? We do know this, don't we? We're in business here. But just for the sake of doing it, what is the derivative of that series? The derivative with respect to x of that series. Not antiderivative, derivative. So I'm really asking you, what's the derivative with respect to x of 1 minus x to the negative 1, right? That's what that is rewritten. Just bring that whole thing up. So take the derivative. Negative 1 comes out.
So 1.
1 minus x to the negative 2 times derivative what's inside?
So negative 1.
Negative 1. And you get 1 over 1 minus x squared. Right?
The derivative is itself.
Or
No,
Or is
no.
that- Okay, never mind.
We
sorry.
are.
Here's what I'm saying, okay? Here's what I'm saying.
I was like, whoa.
This, okay, 1 over 1 minus x squared is equal to the derivative of 1 over 1 minus x. Do you all agree with that statement?
Yes.
Yes? Okay. Now, what is 1 over 1 minus x as a power series? Sum, right? All that? So I'm going to say, but that's equal to the derivative of this power series. Right? So long as what? Absolute value of x is less than 1. Right? I can convert 1 over 1 minus x into this power series so long as the absolute value of x is less than 1. Y'all still agree? Now take the derivative of this power series. What's the derivative of a power series? We just talked about this. This will be equal to, so I'm differentiating now. Sum n equals 1, right, to infinity. N comes down, x to the n minus 1. That's your power series. Let's write out the first few terms, which is, start at 1. 1 plus 2. 2x plus 3x squared plus 4x cubed plus 5x to the 4th plus dot, 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 dot. This function right here, its power series is this. The way I got it was by realizing that this function was the derivative of something I did know about. That's a little tricky.
That requires some thought.
A little bit.
So what would be, it's not as mechanical.
I'm going to do one more slight little thing to this one, all right? Normally, don't our power series start at 0? Yes? Normally, our power series start at 0. That's the way I've introduced them. So although this is a power series, it doesn't look like the general format for a power series, right? Not starting at 0. I'm going to force it to start at 0. So pay attention to this little subtle detail, because I'm going to do it a lot next class. I'll be like, oh, we're going to switch that index over to 0. And you're going to be like, oh, yeah, that's right. He told me to pay attention. And I paid attention. OK, so look. I want to try. I'm continuing this problem here. I'm going to switch my starting index from 1 to 0. Okay? Yes? Now, there's all different sorts of ways that you can teach this. I'm going to try and just show it in a way that I hope it makes sense, but more importantly, it just works. Okay? Watch. See this equation, n equals 1? Right? I really want it to be n equals 0, right? That's my goal, is to get that to become this. So what I'm going to do to make this happen is I'm going to replace n with n plus 1. And somebody tell me why that works.
Because when you go to n plus 1, that's going to be n plus 1, and then that becomes...
Take this equation and replace n with n plus 1, and what happens? N plus 1 equals 1 is what that equation becomes.
Yeah, and
then you subtract 1 on both sides, and you get n is 0, right? So to change my index from a 1 to a 0, I need to basically change my n to n plus 1. But I have to do that everywhere I see it. So this formula now transforms into, I'm going to show all the little detail in this one, n plus 1 equals 1 parentheses n plus 1, x to the n plus 1 minus 1. Everywhere I saw, yes, to infinity. Everywhere that I saw an n, I just put an n plus 1 there. And that's here, here, and there. Those are where I've replaced them. And now, when I rewrite this sum, it becomes sum n equals 0, because I just solved this little linear equation, I get 0. Here, n plus 1, x to the n. There we go. Now, if you start writing out these, like if you start at 0 now, what would happen? 0 plus 1, you get 1. X to the 0, you get 1. Okay, plus, now let n be 1.
You get
2,
squared.
just x, x to the first. And then 3x squared. It's the same series. But I've moved the index around. That will be useful later to be able to move your index around, your starting point.
But you can do that for any number if you wanted your index to start anywhere.
Oh yeah, you could start your index anywhere. But because power series generally start at 0, I want to be able to go back and shift it.
So on the test, did you want us to shift it?
You're going to have problems where in order for it to ever get an answer that makes any sense, you're going to be having to shift indexes within the problem as you're working it. So we're just not there yet. Question? No? That sucks? No. Let's see. I've got about 9 minutes. All right. Next one. Last one for the day. Number 2. Ah, damn it.
Would you take the derivative
Yeah. Would I take the derivative of this?
No, it would be root of.
What? Okay, you want me to take derivative of this?
It's just 1 over that jump.
The derivative of this is what? So I'm just do the scratch work on the side. Okay, you're just thinking about this. What's the derivative with respect to x of natural log of x plus 5?
That'd be 1 over x. 1 over that jump.
This is 1 over
That jump.
x plus 5, which is really 1 over 5 plus x, right? If I start to massage this around, 1 over 5 and then 1 plus x. Do you see I'm starting to make this look like 1 over u? 1/5 x, yes. Do you see? Minus, minus?
Yeah.
You'll see this is actually good.
Yeah.
But it's different than the last problem because we have this. The natural log of x plus 5 is not equal to the derivative of that, right? It's actually equal to the integral of this. Or I'll use this one. The integral of that. Do you agree with that? Yes. I can convert this to a power series. But the next natural question would be, what's the antiderivative of a power series, right? So let's go ahead and put that up on the board. I have enough time. This is still an open question. I kind of jumped the gun. I forgot to put the integration first, tell you the integration first. But at least you can see how we're going to be able to use it, right?
Would it be in terms of
Okay.
E would be better? Or
Let's just make sure, what?
put it in terms of E would be better or no?
Put what in terms of?
To get rid of the natural log and possibly
Mm,
massage it that way?
no, I wouldn't mess with it that way. Because you still, no, you don't really have an equation to be working both sides. I mean, you have f of x equals, but then you're going to be working with the y side instead. All right, term by term integration. We saw with the differentiation that our index had to switch, right, to 1? Remember that? So let's see if it happens with the term by term integration. If we have f of x is c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a to the third plus dot, dot, dot. Remember, this is just sum n equals 0 to infinity c sub n x minus a to the n. All right, that's our general power series. Right? Let's do integration. Let's do integration. If you take the antiderivative of f of x dx, first of all, you're going to have a constant of integration, aren't you?
Yes.
Because you're integrating. So remember, we always did plus c, didn't we? Let's actually write that down first, because we are not going to really have an end to this because it goes dot, dot, dot forever. So I'm going to say plus c. Here's c. That's our constant of integration from integrating. Yes? You know what I'm talking about? Okay. C. Okay. Plus, now let's start taking the antiderivative of this. What's the antiderivative of c naught? C naught x, or c sub 0 x? Yes? Okay. What's the antiderivative of this? Yep, 1/2 c sub 1 x minus a squared. Let's just double check that. If I take derivative of this, right, the 2 comes down, hits the 1/2, goes away. We'll have a c sub 1, and then we'll have x minus a to the first power. That's this. And then this pattern is going to continue. So what do I have now?
So
1/3 c sub 2 x minus a to the third. Then 1/4 c sub 3 x minus a to the fourth plus dot, dot, dot. Let's try and write this as a power series. It's like a big constant, right? It's some constant we don't know, right? Every time you integrate something, right, you always have the constant of integration. Plus c. That's the c I'm talking about. Okay, so we've got this. Can you write the rest of this as a sum? Sum. Where do you want me to start it?
N equals -1, wouldn't it?
Where? What?
Wouldn't it be n equals -1 because we integrated?
We're already at 0, instead of going up 1, it shifts to the left to -1.
Wouldn't it? I think it would be
Well, taking
-1
the
because
derivative, we shift
when
it
you
to the right.
derive it, it's
Like
n
1/2
equals 1.
cn.
It goes from n equals 0 to n equals
What about all this out here? Now, that out there, could you get a formula for that?
1 over n.
Yes?
Yes.
You feel good that you could get a formula for that?
Yeah.
Yes?
Yes.
Now, I think the part that's causing the biggest problem, if there is this piece right here. Why is that piece causing a problem? Because it's x and not what? X minus a, right? Wouldn't it be really nice if this were c sub 0 x minus a to the first power? Wouldn't that be really nice if it was? It is. Why is it? No, a is not 0. We never said a was 0.
X is a, or
No.
or is it 1/2?
What does this plus c mean? That our answer is going to be within a constant, right? Okay. Distribute this through. C sub 0 times x is c sub 0 x. C sub 0 times negative a is some constant, right? And I'm already off by a constant. So if I just replace x with x minus a to the first power, I'm still just off by a constant. And so I can replace this with this.
Just because of trickery?
No, it's not trickery. But if I tell you I'm within a constant and I add 2, right? If I say, hey, plus c, and I just come out here and say plus 2, am I still off by a constant? Yes, but instead I'm gonna subtract c sub 0 times a.
Am I the
And
only
I'm
one-
still off by a
Am
constant.
I the only one who thought that when you said you put COX, C naught X? I thought that as soon as you put that.
They were the only one.
I don't know what everyone else thought. You're asking me if you're the only one? I have no idea. Okay, so if I do this, I'm going to try and start it at 0. The reason I try and start at 0 is because I'd like it to still be like the power series. It starts at 0. Yeah. The C's already taken care of in front. I'm not really looking at this anymore. I'm looking at this because it works. Okay? Now, what's my first part here? 1 over n plus 1 is going to take care of the 1/2, 1/3, 1/4, and in front of this, there's a 1 over 1, isn't there? So that'll take care of that. And then we have C sub n, right? And then x minus a to the n plus 1. That formula works. Do you agree with that? Now check this out.
If you wanted to, could you
What?
could you put that Cn over the n plus 1, or is that?
Yes, you could put the C sub n over
Is
this.
that just because it's a constant? So
The reason why I left it like that is because I wanted you to think about this. If I give you this and I ask you to take the antiderivative, you would ignore the constant and you would say, what's the antiderivative of something to the n power? Like, what's the antiderivative of x to the 7th? 1/8
1/8
x to the 8th, right? In here, the x minus a, you're not going to have to worry about chain rule at all because the derivative is always 1. So this is basically like x to the n power. What's the antiderivative of x to the n power? 1 over n plus 1, right? 1 over n plus 1?
yeah.
X to the n plus 1. It's the same formula that you would expect. The only difference between this and differentiation is that there was no shift in this. We could still start at 0. So with integration, you don't have that danger of forgetting to shift it to 1. Yes?
Now, with you putting the constant of integration out front, how come we're not trying to start at that constant of integration rather? You know what I mean? Like, because when we made up our pattern, we started with the C naught x.
You would like that.
But you had the.
Why didn't I use this?
Why didn't our pattern try to start at the constant of integration? Just because you pulled it out of the summation?
Well, it's kind of like the answer whenever we did that problem.
Yeah, I mean-
1, 2, 7, 2, or 7, 2, 7, 2.
Or am I just overthinking?
I think that would think make it more complicated. This is just some constant. You're never going to know what this is.
So you just put it at the beginning.
Yeah. I put it at the beginning because if I go dot, 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 where do I put it?
Ran out in here.
You see what I'm saying? I can't dot, 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 and then C. I guess I could go dot, 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 C plus C, dot, dot, dot. Right? You know what I'm saying? Because it never stops. Okay, I went over a little bit. Everyone signed in? Make sure you do the homework for power series. Don't worry about the homework for 8-6 yet. Where's the sign in? Oh, you got it here? I think we've actually kind of caught up a little bit here. Wow, we're